A force F is equals to A plus 2x minus bx Newton is acting on a body of mass 4 kg which is moving in a straight line. Wonderful. We have force given as a function of x. Is the body moving in simple harmonic motion? Is the body performing simple harmonic motion? If yes, find the equilibrium position of the particle. So first of all, we have to see whether there is simple harmonic motion or not. And then if there is simple harmonic motion, then what is the equilibrium position x naught? This is the question. Now, if you want to tally whether there is simple harmonic motion or not, you have to see the standard equation of force in case of SHM. What is force as a function of displacement in case of SHM? Tell me the standard equation. You would say force, if it is minus k times x minus x naught, then we will have an SHM where x naught is the equilibrium position and k is just a constant. All right. So this is the standard equation of force in case of SHM. Now let's see what equation do we have in our question. In our question, they say force is A minus B minus 2 times x. This equation was given in the question. And we can see that if you take minus b minus 2 as common, then we have x minus a divided by b minus 2 left in a separate bracket. Okay, so we can write this equation as the equation of force given in our question. Right? Right. Now let's tally the two equations. You can see the equations are of same format. That is, we will have an SHM and k can be written as b minus 2 and x naught, the mean position, can be written as a divided by b minus 2. So the equilibrium position of SHM given in our equation is x naught is equals to a divided by b minus 2. So this equation of force contains everything. It contains k, it contains x naught. We just have to find that. So x naught we got a divided by b minus 2. And we can see in option D we have the exact value. So option D is the right answer for our question. A block of mass 1 kg is connected to a massless spring of force constant 100 Newton per meter and it is placed on smooth horizontal surface. So look at the figure. You can see the block and you can see the spring. At t is equals to 0, a constant force of 10 Newton is applied on the block when the spring is in its natural length. The speed of the block when it is displaced by 8 centimeter from its mean position will be. Very interesting question. So when the distance of the block from the mean position is 8 centimeter, what is the speed of the block? And these are the options. Again, let's see the question. The speed of the block when it is displaced by 8 centimeter from its mean position. Now, what do we mean by mean position? The mean position is the position at which the net force on the object will be 0. So you can see there is some force 10 Newton which is applied on the block and this force is constant. But there will be some spring force also. So let's say the mean position is x is equals to x naught. So when there is a force k times x naught being applied on the block by the spring in the backward direction balanced by this 10 Newton force, then these two forces cancel each other out and we will get the mean position x naught. So mean position x naught is written as 10 divided by k. K was given to be 100. So we have the mean position as 0.1 meter. Right? Right. Now you can get the mean position in another way also. Let's try to write the general equation of force on the block. So let's say the object is displaced by a distance x from this position. At this position, the velocity of the object was 0. Right? Right. Now what is the net force on the object? You would say, well, one force is 10 Newton in the forward direction. In the backward direction, there is spring force kx. And this force can be written as minus k times x minus 10 divided by k. Right, exactly. And now I will disclose to you that this object will perform a simple harmonic motion. Believe it or not, the object will perform a simple harmonic motion. You will ask why? See why. If force is of this form, minus k times x minus x naught, then the object performs a simple harmonic motion, where x naught is the mean position. Alright? Alright. Now, let's compare these two equations. This equation, f is equals to minus k times x minus 10 by k. And this equation, f is equals to minus k times x minus x naught. So can you see what is x naught? X naught is equals to 10 by k. Let me write it over here. X naught is equals to 10 by k. Yes, we can see. And when we place k is equals to 100, we will get x naught as 0.1 meter. So this is how you can find the mean position. And the object, as it is performing simple harmonic motion, its speed square, v square, speed square can be written as omega square times a square minus x square. So this is the equation which relates speed and displacement from the mean position. Now, what did we have to find in the question? We have to find what is the speed of the block? What is the speed of the block if it is displaced 8 centimeter from the mean position? So, if x is equals to 8, if x is equals to 8 centimeter, what is the speed of the block? This was the question. Now, you would say that when we place everything in terms of centimeter, we will get this equation. Yes. And what is A? A is the amplitude. Okay. So, can you guess what is the amplitude? You would say, well, we can guess. This is a simple harmonic motion, right? Right. Now, in simple harmonic motion, we can see at extreme position, the speed of the block becomes 0. Okay. So, this position at which the speed is 0, this starting position at which the speed is 0 is one of the extreme position. Okay. And the object will reach the mean position if it is moved by a distance of 10 centimeter or 0.1 meter. So x naught, we have calculated. X naught is 0.1 meter or 10 centimeter. So the object reaches the mean position, and then if it is further displaced by another 10 centimeter, it will reach other extreme position. Alright, then the object will come back and this to and fro motion will be simple harmonic motion. Alright, now we know what is the amplitude. Amplitude is nothing but 10 centimeter. Amplitude A is equals to 10 centimeter. Now let's just place 10 over here. We have 10 square minus 8 square. What is this? 100 minus 64 is 36. So we have omega square times 36. What is omega? Can you tell me what is omega? You would say, well, we remember a formula of omega. Okay, tell me the formula. The formula for calculating angular frequency is nothing but under root k by m. Right. So what is k? K is 100. What is m? M is 1 kg. So under root 100 by 1. This is nothing but 10. So what is omega? Omega is 10. Right. So we can place omega as 10 over here. 10 square times 36. This is v square. And you can see the speed of the block v. It is coming out to be 60 centimeter per second. Note, we have used centimeter as our units. So we got this speed. Now, velocity of course have plus minus signs, but let's talk about the speed. Speed is 60 centimeter per second. And we can go and mark option C, 60 centimeter per second, as the right answer for this question. The potential energy of a particle of mass 1 kg moving along the x-axis is given as u is equals to 4 times, in bracket we have 1 minus cos of 2x, where x is in meters. Now we have to find the time period of small oscillation. Now something interesting is there in the question. We know potential energy as a function of x. and they have asked us to find the time period. And they have also written small oscillation. That is, x is really, really small. So, how to find the time period? First of all, we must know whether we have SHM or not. So, let's find that out. The standard equation of force in case of SHM is minus k times x minus x naught. And when the mean position is at x is equals to 0, then the equation of force is F is equals to minus kx. Let's see, are we getting this form of force in our case? So in our case, potential energy is given as a function of x. Can you tell me how to obtain force from the potential energy function? How do we obtain force from the potential energy function? You would say in our case we have potential energy as a function of x, right? So force is minus du by dx. Very nice. This is the force in our case. So we can see that force would be minus 4, and then we differentiate 1 minus cos of 2x with respect to x. All right. Now, this differentiation of 1 is just 0. And differentiation of cos theta with respect to theta is minus cos theta. So, what are we getting? We are getting minus 4 times. Now, we have minus sign. Minus sign is there in front of cos. And then, when we differentiate cos of 2x, we will get minus sine of 2x. Then we differentiate 2x. So its differentiation will give us 2. So this is what we are getting. Now this thing is written as minus 8 times sine of 2x. This is our force. So force is minus 8 times sine of 2x. F is equals to minus 8 sine of 2x. Now the standard equation of force in SHM is like this. F is equals to minus kx. But this is not matching with our standard equation of force. What should we do? We don't have a SHM. But you see in the question they have said small oscillation. That is the trick. So when x is very, very small, we can apply some approximation. And you have the approximation if x is small. Then sine of 2x is approximately equal to 2x. When theta is small, sine theta is approximately equal to theta when theta is small. So we have this awesome approximation. Now if we apply this approximation, we can see our force is minus 16x, right? And this matches with our equation of simple harmonic motion force. Now, once you know force as a function of x, can you find acceleration as a function of x? Yes, we can. Acceleration is, after all, force divided by mass. So, acceleration would be given as minus 16x divided by mass. Mass was 1 kg. Object was of 1 kg mass. See, in the question they have said mass is 1 kg. All right. So, when we divide force by mass, which is 1 kg, we get acceleration. Acceleration is minus 16x. Now, the standard equation of acceleration in SHM was A is equals to minus omega square x. Remember? Remember. Now, what is omega? Can you tell me what is omega? Yes, we can. All right. What is omega? Omega is nothing but under root 16, which is 4. Very nice. Now, we have to find the time period. What is the formula of time period? You have to tell me. What is the formula of time period? Time period is 2 pi by omega. All right, very good. So, in our case, time period would be 2 pi divided by omega. Omega was 4. So, time period came out to be pi by 2. Yes, time period is pi by 2 seconds. In pi by 2 seconds, object will complete one full oscillation. So let's see. Option C is the right answer for our question. A block of mass 100 gram is attached to the spring of spring constant 100 Newton per meter. That's so awesome. We can see the block. The block is moved to compress the spring by 10 centimeter and released on the frictionless floor as shown below. So what do? We push this block and compress the spring like this. And we compress the spring by 10 centimeter. Okay. And we release the block. What will happen to block? Block will come to the mean position like this. But when it comes to this position, it will have some kinetic energy. So it will try to move on the other side. If the wall was not present, then it would have moved 10 centimeter on the other side. But there is a wall. So what will happen? Block will go and collide with the wall. Bam! And then after collision, it will come back. Ooh. So this is the motion of the block. Question says, if the collision with the wall in the front are elastic in nature, then find the time period of motion. So what is the time period of this motion? This is a short motion, so it will have a short time period. Let's call the time period to be t dash. So what is this time period t dash? This is the question. Okay. And these are the 4 options. All right. Now, let me tell you, you can find the time period when there is no wall. You would say, what's the big deal in that? We know if the block moves 10 centimeter like this to the negative extreme and then comes back to the mean position again by traveling 10 centimeter and then goes to the positive extreme again by traveling 10 centimeter, come back to the mean position again by traveling 10 centimeter. We have one complete simple harmonic motion. Yes. And in this simple harmonic motion, you can see the time period of SHM is 2 pi under root m by k. Right? Right. What is mass? Mass we know is given in the question 100 grams. We can write it as 0.1 kg. And what is K? K is written as 100. All right. So when you calculate, this thing will be about 0.198 seconds. You can also call it as 0.2 seconds. All right. So we know what is the time period. Now you can see we can divide this simple harmonic motion into 4 equal segments. That is, from extreme position to the mean position, from the mean position back again to the extreme position, from extreme position back again to the mean position, and from the mean position back again to the extreme position. So these are the 4 equal segments, and in these segments time taken would be equal. So from extreme to mean, time taken would be t by 4. Right? Right. Now, let's go to our original situation in which we had wall. So, if there is wall, what would happen? Now, let's see the motion from this position. So, the block will move from this extreme position to the mean position. What is the time taken? It is t by 4. All right. Now, from the mean position, when the object reaches the wall, the time taken, let it be t naught. Okay? Okay. And then from the wall back to the mean position, let the time taken to be t naught. All right. And then from this mean position to the extreme position, time taken is t by 4. Right? Right. And this motion will repeat again and again and again and again. So, time period t dash is nothing but twice of t by 4 plus twice of t naught. Right? Right. So, we have to calculate this time period t dash. Now, we must know what is the value of t naught to calculate this time period t dash. Right? Right. So, shall we calculate t naught? Okay, let's begin. Now, how do we calculate t naught? Now, let's say when the object is at mean position and it is performing simple harmonic motion, its equation of SHM can be written as x is equals to a sine omega t. Is it right? Right. So, when we see the particle at mean position at t is equals to 0, we can write this equation of SHM. But this is the equation when we don't have any wall. All right, we understand. But we have to find the time from the mean position to the wall. Okay? Okay. Now, at the mean position, x is equals to 0. When t is equals to 0, x is equals to 0. When t is equals to t naught, When t is equals to t naught, what is x? X is a by 2. All right. So this thing is a by 2 is equals to a sine of omega t naught. All right. This will give us t naught. So smallest positive value of omega t naught is coming out to be pi by 6. And what can we write in place of omega? Give me something in terms of time period. Omega is equals to 2 pi by time period, right? Right. Now instead of omega, I will just write 2 pi by time period capital T. Pi gets cancelled out, bam, bam, and we get T naught. We get T naught as T naught is equals to T by 12. Yes. So time period, complete time period T by 12 is T naught. So let's put this value of T naught over here. What are we getting? T by 2 plus T by 6. Yes. And we can see that this is 4T by 6, which is 2T by 3. This is the new time period T dash. It is 2 times old time period divided by 3. When the wall was not present, the old time period, we remember. What was that value? That value we have calculated. It was 0.198. So let's put this value over here. So we are getting T dash. This thing, T dash is coming out to be 2 by 3 times 0.198. And what is this? This is about 0.132 seconds. So we have calculated what is the time period. It comes out to be 0.132. When there is wall, this is the time period, 0.132. Now let's go and mark option D as the right answer for this great question. Molten wax of mass small m drops on a block of mass capital M, which is oscillating on a frictionless table as shown. Select the incorrect option. Now we have an awesome block, capital M. It is oscillating. It is performing simple harmonic motion on smooth surface. And we bring a candle and we drop some wax on this block. The wax goes and sticks to the block. There is inelastic collision. All right. And we have to choose the incorrect option. The incorrect option. Don't choose the correct option. Otherwise, we will make mistake. So option A. If the collision takes place at the extreme position, amplitude does not change. If the collision takes place at the mean position, amplitude decreases. So these two options deals with amplitude. And option C, if the collision takes place at the mean position, time period decreases. And if the collision takes place at the extreme position, time period increases. So these two options deal with time period capital T. All right. So let's talk about time period for a while. What is the time period of SHM when we have spring and mass? Tell me the time period. You would say, well, the time period, if we remember it correctly, was 2 pi under root mass divided by K. Yes, this was the time period. Now, are we increasing the mass? When we drop wax, are we increasing the mass? Yes, we are increasing the mass. So if mass increases, what happens to the time period? Time period also increases, right? So whether we drop the mass when the object was at mean position or at extreme position, in both the cases we are increasing the mass, and time period depends on the mass. So time period increases. Position does not matter. If mass increases, time period increases. All right. So in our case, time period will definitely increase. It won't remain the same. It won't decrease. It will increase. So let's read the options. Option C. If the collision takes place at the mean position, time period decreases. Will it decrease? No. It will increase. So option C is false. Option D. If the collision takes place at the extreme position, time period increases. Yes, time period will increase. Although the position does not matter, but in case it is written time period increases, it is true. Right. Now, let's try to find out A and B, whether they are true or false. So these option deals with amplitude. Now let me tell you something interesting about amplitude. The total energy in simple harmonic motion, the total energy, if the potential energy you take potential energy at origin to be 0 or potential energy at the mean position to be 0, if you have this condition, then the total energy can be written as half k a square, right? Right. So total energy depends on amplitude and amplitude depends on total energy. All right. So if we are not changing the total energy, we are not changing the amplitude. If we are changing the total energy, we are changing the amplitude. Okay. So let's see. Option A says if the collision takes place at the extreme position, amplitude does not change. So if we drop wax at the extreme position, are we changing the energy? Well, you can imagine. This object reaches the extreme position. What is the velocity at the extreme position? Velocity is 0. All right. So just before the collision takes place, velocity is 0. And just after the collision takes place, velocity is again 0. So we haven't changed the energy. We haven't changed the kinetic energy and we haven't changed the spring potential energy. So we haven't changed the total energy. So if total energy is not changed, the amplitude A would not change. Okay? Okay. So option A is true. Amplitude does not change when we drop the wax when the object was at extreme position. Right, it is true. And B, if the collision takes place at the mean position, amplitude decreases. Now, what do you think will happen when the collision will take when the object is at mean position? When the object is at mean position, does it have any velocity? Yes, it has. It has the maximum velocity. Okay. So let's imagine the object to be moving with V naught. Now, when we drop the other mass on this block, there is some inelastic collision, right? Inelastic collision. Yes. And in case of inelastic collision, we can see the horizontal velocity of this mass small m was 0. So this horizontal velocity was 0. And if we have an inelastic collision, then we can see there will be some decrease in kinetic energy, right? Right. In case of inelastic collision, there is energy loss. So energy will decrease. Energy will decrease. If there is decrease in energy, there is decrease in amplitude. So in that case, energy decreases and amplitude also decreases. So B said if the collision takes place at the mean position, amplitude decreases. This is perfectly true. So A, B and D are true and C is false. And we had to pick the incorrect option. So we pick C as the answer for our question.